Here's one more example from the homework of revolving around an offset axis. It's a little bit of a harder problem. They don't actually expect you to finish it off, but they want to get you to the setup. And I think just getting the picture drawn is the hard part. The region is supposed to be between x squared minus y squared equals 1 and x equals 3. And then we're going to revolve it around the line x equals minus 2. Well, x squared minus y squared equals 1. We talk about this in pre-cal, and then we drop it. We don't do much with it, unfortunately. But here it comes back. It's a hyperbola. Hopefully that's a little bit of recognition. In that hyperbola, if you actually graph it out, it's going to have an intercept at x equals 1, y equals 0. And then it's going to go off to the right, up and down. And it keeps going off and actually is asymptotic to a straight line. But then it hits this x equals 3 line. And so, again, that can be a bit of a stopper if you've forgotten how to deal with these guys. Again, even if you've never seen this before, you can start plotting points and get somewhere with it. But as long as you just know that it's this kind of bowl shape opening to the right, that's all we really need for the qualitative picture. And then it's going to hit x equals 3. Oh, that's a 3 there. And then, so it's going to be this region in here that we're going to revolve around this line. Whoa, okay. One thing I discovered when I sketched this, and this is a very typical thing, is that that's not going to fit on my picture real well. And so I redrew that with a little bit more room. Here's the axes, so here's the origin. Here's that region. Oops, I can bold that in there. So here's the region that we're filling in, and then we're revolving that around. Okay, so this is a thing we've seen before, is that we're getting a cylinder, but then with a heck of a lot of stuff scooped out. So what we're basically kind of getting is a weird kind of donut shape. One way good way to think about it is take a full kind of donut shape. If you took some sort of vaguely circular thing and revolved it around, you'd get a donut shape, what mathematicians call a torus. And then we're kind of cutting away the outer part of that. We're taking a cylindrical cutter and cutting away the outer part of it. So this part in here revolved around to make the sort of the inner part of a donut shape. And all this stuff in between is not part of our region. That's exactly what a huge, huge hole in the middle. So let me go ahead and use this as the 2D picture. What are we doing? We're taking a strip like this and revolving it around, and that's what makes a typical washer shape. So all this stuff in here, the flat washer shape with typically a rather large hole in the middle, those are the slices we're going to be adding up. Okay, so let's do our usual story of volume is the sum of the bits of volume. Each bit of volume is a slice. Now what's our variable? Again, because it's revolving around a vertical axis, it's the slices are labeled by how high they are, the vertical coordinate, so that's a dy again. And now they are washer shapes. Again, the third version of this picture. Remember, I like to combine the full 3D picture, the 2D picture, and also just a little schematic picture of what kind of shape do we have for one of those slices. It's going to be a washer shape where it's all this stuff. This kind of shape goes in, slices into here. So that's going to be pi big R squared minus pi little r squared. And that's where we really have to look at the particular case involved. So little r and big R, those are always the radius of that, the distance from the inner curve to the axis, and the distance from the outer curve, which in this case is a straight line. And I like to be able to put those on a simpler picture, and it's always going to be this. You're looking at that strip, and you're really describing where is that strip. How does it sit in relation to the axis of revolution? There's an outer end of it, furthest away from the axis, an inner end closest to the axis, and those are the big R and little r. Well, those are x different distances. Those are distances along an x number line. So they're going to have to do with x's, but we want to get it in terms of y, because that's our variable of integration. So let's go back to this picture and do that carefully. This picture here. So here, little r, actually big R is easier. That is a constant. It's a cylinder. It's just always 3 minus a minus 2. That's a 5. So that's nice. Sometimes that's constant, sometimes not. And then little r, that's the difference between this x value and minus 2, where it's that x value that's on that curve. And that's where we have to solve here. Okay. So that's going to be x squared is 1 plus y squared, or x is the square root of 1 plus y squared. And so that's going to be square root of 1 plus y squared plus 2. And so now we're ready to put this in. This is pi. I'm going to factor out the pi here. Times 25, that's the 5 squared, minus the square root of 1 plus y squared plus 2 all squared dy. And that's not an impossible integral to do, but it's kind of beyond what we're set up to do with AB Calc methods. Oh, and we still need to get the limits, but that's not too bad. We still have to do a little bit of algebra there, though. It's, again, back to this picture. The limits are really here. What's the smallest value of y? What's the biggest value of y that we can get? And that, as usual, comes from intersecting these two guys. So if x is 3, we get 9 minus y squared is 1. Y squared is 8. Y is 2 root 2 plus or minus. So minus 2 root 2 to 2 root 2. Fairly ugly expression by our standards. Not at all ugly by the standards of people who do this for a living, to be honest, but definitely something that we can appreciate, that they just wanted us to set it up and not evaluate it. But the steps are really the important thing for me. And again, the thing I like to emphasize is these 3 pictures and the role of transferring the information between the pictures and getting, especially back down to this picture, which is where the minus 2 root 2, the 2 root 2 came from, which is where this stuff came from. Almost all of it really comes from this picture and then combined with our standard sequence of steps for the setup.